In this video, we will describe the approaches implemented in this project. First, we tried heuristic search and we mainly used the A-star search algorithm in this approach. The core design idea for this approach is to find a new goal state based on the current game state, then use A-star search to find the shortest path to the goal point. In every step, the goal state will be recalculated and updated so that the agent can choose the best action it will take in the next step. We divide the two agents into two parties, one offensive party and one defensive party. The two agents perform actions individually and there is no communication between them. The offensive strategy is when the attacker doesn't carry food, its goal is the nearest food in the enemy's side. When the attacker eats the food, his goal state will change to the nearest point in its own side, and that means it will return. And in the whole process, the enemy position will be considered. The attacker will run away from the enemy to prevent the enemy ghost from eating it. The defensive strategy is that the defender will initially move to the center in its side, and when it doesn't find an enemy, it will also move to that position. When an enemy invades into its area and is discovered, the defender's goal state will change to the nearest enemy's position. Then using the A-star search to calculate the shortest path to the enemy and then eat it. When we're doing this project, there are mainly two challenges. The first one is timeout problem. As the result showed a large number of fail cases at the first test, because A-star will reselect the goal and perform calculation at each step. This process can be very time-consuming. Therefore, we added a time limit to the A-star search and the fail cases decreased greatly. The second problem is that if we are in the red side, our program can perform well, but in the blue side, we often lose the game. So we considered the situation when we on the blue side and made some adjustment to the goal state, and the final result was improved. In this approach, we don't take into consider the capsule, and each time the offensive agent just eat one food and it will return. So in the future, we will consider the capsule and adjust the eating strategy of the offensive agent. In the practical implementation, we observed some benefits and pitfalls of this approach. From the observation of several winning games, the offensive agent is not greedy. Each time it just eats one food and returns, it reduces the probability to be caught by the enemy. From the observation of several tag games, the goal state selection is not so intelligent, sometimes will cause a deadlock with the enemy team. My team cannot get into the enemy's side and the enemy cannot get into my side. Besides, we analyzed the several losing games. The defensive agent is a little dummy. It will move only when the enemy invades in its side and will not follow the enemy on the edge. So sometimes it cannot well defend the food.
The second method we're using is the Monte Carlo search tree. When we were doing our research on the Pacman contest, we found that there's a lot of games, including the ordinary Pacman game, have AI built into it using the Monte Carlo search tree and have good performance. So we think that it may be a good idea to implement Monte Carlo search tree in our AI to dodge enemy ghosts and catch enemy Pacman. But how is it done is the question. We all know from the class that there are 4 major steps in Monte Carlo search tree, which is selection, expansion, simulation, and backpropagation. In the selection step, we choose the current position of our agents as the founder node and build a search tree. In the expansion step, we expand the search tree by exploring the successors of the founder node, which is the possible position in a few steps. In the simulation step, we'll try to locate elements in the game, like enemy ghost, enemy Pacman, food, capsule, and so forth, and give a score to the node accordingly. In the final backpropagation step, all the scores will sum up and return to the possible actions, and the system will choose the action with the highest score. We found out that the Monte Carlo search tree runs pretty fast with this setting. We didn't assign an elapsed time for the program, but instead exhaustive search is used for the future 3 steps of our agents. The most challenging part of setting up Monte Carlo search tree is to decide how the scoring system works. Because how much score will you assign to the enemy ghost, enemy Pac-Man, capsule, and food and so forth will affect how your agents react. If the score is not well designed, well, yeah, GG. But after 100 times of turning, we found a pretty good combination. We also designed some strategies for the agent to apply. For example, when being chased, avoid food, but get capsule. Another strategy is when we are scared, our agent will attack. There are other strategies too, but we don't want to give it out for now. So, to sum up, our second method is to use Monte Carlo search tree as the core and pair it with strategies.